Ladies and gentlemen, welcome to your Chapter 22 lecture for Physics 1. Today we're going to be talking about electrostatics. To begin with, I really wanted to start this week with a demo of this device, this thing we call a Van de Graaff generator. But unfortunately, the one sort of caveat to trying to use a Van de Graaff generator for demonstrations is that whether or not it's actually going to work depends completely and totally, almost entirely, on the humidity in the air. If it's too wet, then we have a real problem trying to make it work. And unfortunately, it's been raining this weekend, so we're kind of out of luck on this one today. My apologies, ladies and gents. In order to make it up to you, however, I posted a link to a video on the Chapter 22 lecture page where you can see all of the things that I wanted to show you, the pie pans, the Rice Krispies, all the good stuff is in this video, the Van de Graaff generator. Let me just spell it out for you. It's Van de Graaff generator. So, you can either look at the video that I posted, or you can look at another one. Please pause right now and go and look at that before we continue on any further. Now, once you watch the video, hi Ninja. Once you watch the video, go ahead and try and answer and tell me why it is that one pie pan on the top flipped before the rest. What kind of charges did the pie pans have? Obviously there's some electric something going on here, right? Some static electricity. We all know what that's like because we've all pulled things out of the dryer before, right? So what could it possibly have been? Well, to answer these questions, we have to begin with the very fundamentals. And probably most of us learned the basics of this back in grade school. The most simple fundamentals of electricity are that charge comes in two varieties. That, of course, is positive and negative. These charges live in things like atoms. These subatomic particles that have these charges are called the proton. Whoops. Sometimes we just write it like this, like a P+. And the negatively charged particle is called an electron, which sometimes we write like this with an E-. There's a third type of subatomic particle, of course, which has no charge. This thing that we call a neutron, because it's electrically neutral. Let us remind ourselves of the structure of the atom very briefly, shall we? Let's take, for example, the helium atom. Now, if we remember, the helium atom has two protons in the nucleus, right? And there are also, in the stable isotope of helium, two neutrons in the nucleus as well. And then out here in the ground state orbital are two electrons. That's the sort of basic, what we call the Bohr model of the atom for the atom, and in this case the helium atom. Now in the center is an area that we call the nucleus. Whatever. In any case, the particles that live here in the nucleus are much more massive than the rest of the particles, that is, the electron. The proton and the neutron have a similar mass, almost 2,000 times as much as the electron, about 1,800 or so. But this is review, we know this already from our study of atoms from the previous chapter. In any case, the electrons live out here, as we also discussed before, in these quantized energy states, these electron orbitals. Now the book says that the preferred term is something we call a shell, but that's not true at all. That's a holdover from a time when we used to think that there was this funny configuration called the octet rule, where the outer shell of an electron, or the outer shell of an atom, always had 8 electrons in it. But as we know now, that's actually like this, the ground state orbital with 2, and the next one, the next orbital on the outside that has 6. And so it kind of looks like there's 8, but it's actually 2 separate orbitals. In any case, this proton is identical to that proton. And indeed, they're identical to all the other protons in the universe, all the ones that are in your hand, in your shoes, whatever. The same thing is true of all of the neutrons in the universe, and you probably guessed it, all of the electrons in the universe. The magnitude of the charge on an electron, while negative, is the same in magnitude as the charge of the proton, although this one, of course, is positive. Atoms occur in nature electrically neutral. That means, since the electron and the proton have the same magnitude of charge, that as they occur in nature, they have to have the same number of protons as they do electrons in order for them to stay balanced and electrically neutral. Now, why is it that if like charges repel, that these protons here in the nucleus don't cause the nucleus of this atom to just fly apart and disintegrate? Well, that's because of something that we call the strong nuclear force. That is one of the 4 fundamental forces of nature. And we'll come back to that in chapter 32. Regardless, there is a symmetry in nature here. The amount of charge in the universe has to remain basically constant. Just like matter and energy, momentum, all that stuff, right? All of that, basically, the amount of that in the universe remains constant. And so we say that there is a law of conservation of charge also. Now it's true that an individual atom can gain or lose charge. If this gained an electron, it would become negative, right? Right now it's electrically neutral because it has 2 protons and 2 electrons. But if it gained an electron, maybe out here in its next orbital, that it would become negative overall, right? If it lost one of these electrons, right, so it only had 1, it would become net positive, because now it has 2 positive charges and only 1 negative. So it is true that an individual atom can gain or lose charge, becoming an ion or becoming ionized, as we say. However, that electron went somewhere, and the total amount of charge in the universe still stays the same. And so charge is a conserved quantity. Sometimes these subatomic particles can become other subatomic particles through processes like beta decay, but we'll talk about beta decay later on when we talk about radioactivity. Electrons can also move in between atoms. For example, if you have like a metal, it's really easy to conduct electrons across, say, a gold trace like in your computer or in your phone. And as a result, it's really easy for a current to pass, but we'll talk more about that also in the upcoming lectures. Now, if you pet your cat a little bit, or you pull a sheet out of a dryer, you're going to pick up electrons from it and get a little bit of a static electric charge. But this does not create electrons, it just moves the electrons from one place to another. We call this charging by direct contact. We said at the beginning that opposite charges attract and like charges repel. We all probably learned that one in grade school, right? Opposites attract. Now the force that governs this interaction is something that we call Coulomb's law. I'll spell it, don't worry. We've probably never heard this word before this course, right? And so it would be unfair of me to just assume that you know the right way to spell it. But don't worry, this is not a course in English, so you're not going to be asked to spell this for a midterm or an exam or whatever. In any case, the expression that we have for Coulomb's law is the force of either electrostatic attraction or repulsion in between two charge configurations. It looks something like this. There's this thing K, which is just a number. We used to write it this way, 1 over 4 pi, and this is the permittivity of free space. This is how easy it is for like an electric field or something like that to go through the vacuum of space. This is something like 9 times 10 to the power 9 Newton times meter squared per Coulomb squared. I'll explain this unit in just a minute here. But regardless, it's charge 1 times charge 2 divided by the distance between them squared. Now, Q is what we use for charge. That's like an electron or a proton or a bunch of electrons or protons together or what have you. A charged piece of material. Where Q is the magnitude of the charge, or how strong the charge is, how many positive or negative charges are in it, that kind of thing. You'll notice this 1 over r squared dependence. Does that look like anything familiar? Everybody remember minus g m1 m2 over r squared, right? The law of universal gravitation. Newton's law of universal gravitation. Now, this 1 over r squared, this meant that gravity would extend out into the universe equally in all directions or spherically. Just like the influence that either of these charges are going to have on the universe around them, those are also going to expand out spherically. And as we're going to see, that's the electric field. But regardless, the distance in between these two charges matters, just like the force of gravity in between two masses that are attracting each other. Now, if, let's say Q1 is like an electron and it's negative, and Q2 is an electron, or excuse me, a positron or a proton and it's positive, right? That means this whole expression, this force is going to be negative, and very much like this thing here, right, where we have a minus sign in front, that means it's going to be an attractive force, seeking to make the distance smaller. However, let's say that now we have two negative charges. Well, negative times negative is positive, right? And so these are going to have a positive force on each other, and they're going to push each other away from each other. The same is true, of course, if you have two positive charges. Now, we haven't really talked a whole lot about charge, and while it's tempting to think that the SI unit for charge is what we call the elementary charge, or the amount of charge that's on either a proton or an electron, unfortunately that is just not true. The SI unit of charge is something called a coulomb, and that's 1.602. I'm sorry, 6.24. I'm thinking the other way. It's 6.24 times 10 to the 18 elementary charges, or like the charge on the electron or a proton. That also means that one electron or one proton has 1.602 times 10 to the minus 19 coulombs. We usually use the letter C for a coulomb. So just like gravity, if the attractive force is negative, then it'll seek to draw these two objects together. Now, I had also really wanted to show you a demonstration of if you take a balloon and you just rub it on your sleeve a little bit, you can just stick it on the wall and it'll sit there. But unfortunately, I don't have any balloons here and we're on shelter in place. However, I did leave a link to a video where someone has done exactly that with a balloon and just rubbed it like on their sleeve or something and stuck it on the wall and it sits there. Now, why could that possibly happen? This may be a good time for you to pause this video and go and watch the other one. In any case, when you get back, why did that happen? Well, if you took like a piece of fur and you rubbed it on the balloon, it would become negatively charged, right? Because the electrons from the fur would end up on the balloon. Just like if you pet your cat, you know, you get a little bit of a static electric charge. The wall is going to be electrically neutral, right? So if we got a wall here, there's going to be some positive charges and also some negative charges, right? You can't exactly just plug your phone straight into the wall, right, to expect it to charge. It doesn't work that way. You have to plug it into an electrical outlet. So basically there's the same number of positive and negative charges in just about everything. The wall, the floor, your shoes, your arm, whatever, right? Now, if this balloon comes near it, and this balloon has a bunch of negative charges on it, what's going to happen when the balloon comes near the wall? Well, as the balloon comes near the wall, we've got a bunch of minus signs here. It's going to attract all of the negative charges, or excuse me, all of the positive charges in the wall and repel all of the negative charges. And so while the charge on the wall doesn't actually change, and neither does really the charge on the balloon, the charges in the wall become what we call polarized. So this is polarization. Materials that hold on to their electrons really tightly and don't like to conduct electricity are what we call insulators. And that's maybe a little bit different from what we talked about before. Things that don't transfer heat as well are often called insulators. But believe it or not, sometimes, very often, they're kind of the same material. Things that don't conduct electricity very well often don't conduct heat very well either, like styrofoam. Materials whose electrons can move between atoms easily are usually called conductors, things like metals. And metals also conduct electrons and heat pretty well, right? Some materials are able to conduct electricity with zero energy loss, and these are what we call superconductors. And it's been the subject of a lot of scientific advancement as of late, us trying to figure out how to make what we call room temperature superconductors, or superconductors that operate at normal temperatures, not like super sub-zero temperatures like you have to do with, if you want to make, say, copper into a superconductor, it has to be at really, really low temperatures, way, way below freezing. There's another kind of material, however, called a semiconductor. A semiconductor is somewhere in between a conductor and an insulator. Because they have sort of special properties, they can do things like conduct electricity only in one direction. There's an electric circuit component we call a diode that we usually draw this way in a circuit to show that current can only actually go one way. It can't go the other. And so we use things like semiconductor materials to make things like diodes, which is like an LED. LED stands for light emitting diode, or to be used as like switches to control the flow of current. These are typically made by adding toxic things like arsenic or phosphorus to an insulator like silicon, so it can kind of conduct electricity, but not as easily as some like a conductor or a superconductor. Okay, now let's say that we have two metal spheres. Okay? And let's say that they are in physical contact. Now let's say that normally, right, they have the same amount of positive and negative charges, right? But let's say that you took like a glass rod or something and you charged it by rubbing some animal fur on it or on your sleeve or whatever, right? And so this negative rod here, or this glass rod, is going to have a bunch of negative charges on it. And as this glass rod gets brought near these spheres, what's going to happen? Well, polarization would suggest that the positive charges are going to get attracted to the negatively charged rod, whereas the negative charges are going to get repelled, right? And if we're talking about two metal spheres, they're going to conduct the electricity very easily, and the negative charges are going to be able to migrate very easily, right? Now, if we separate them while they're in this kind of configuration, so we got one here, and we'll move this one way over here, right? Now this one's negatively charged, and this one's still positively charged. And if we move this rod away, now we have a positively charged sphere and a negatively charged sphere some distance away from each other. We call this induction. The greater the charge, the more of an electric force that the charge can generate. We call the space around a charge where it can exert a force an electric field. And it's because of the electric field of this negatively charged rod that it was able to exert its influence on these spheres even though it didn't actually touch them, right? Now the book literally calls this an aura, which is some weird hippie stuff. So regardless of whatever the author thinks, there isn't some kind of magical field of unicorns or ghosts or Pokemon or whatever around it that causes electric charges. The electric field is defined to be the force per unit charge that a charge can put out into the universe. The SI unit, then, for the electric field, because we're talking about the amount of force per unit charge that it can make. This is newtons, right? The SI unit of force is newtons. Everybody remember what the SI unit of charge is? That's right, coulombs. And we often express it this way. K, remember our constant, this is 9 times 10 to the minus 9 Newton meters squared per coulomb squared, that K. Times Q, which is the magnitude of the charge, over R squared. You'll notice that the equation for the electric field, or the expression for the electric field, K times Q over R squared, we're just missing another Q, and that's an electric force, right? And so really, the electric force can be thought of as the interaction of two electric fields when two charges exert their electric field on each other. Now by convention, we've decided that electric field lines, or if you wanted to draw an electric field, electric field lines start on positive charges. So they would like go out here from from this positive charge, right? And they end on a negative charge. So an electric field in between these two charge elements here might look something like this. If we want to think of this in terms of potential energy, that goes something like this. We call this phenomenon electric potential by a special name, voltage. And it's not quite the same thing as potential energy. Electric potential is the amount of work per unit charge that the electric field can do. The unit of electric potential is the volt. usually denoted by a capital V. If a charged particle comes near a high amount of electric potential, like a bunch of charge or something like that, then the electric field can do work on the charges and move them. Just like if you have a positive and a negative charge near each other, they're going to attract each other. The unit of volt is the same thing as work or energy over charge. So the unit of work or energy is, if you remember, the joule, and the unit of charge again is the coulomb. So volts is joules per coulomb, if you want to think of it that way. Now if a charged particle comes near a high amount of electric potential, then it'll exert a force. That's what it really means. Now if you look at a battery like a AA, a AAA, a C cell or D cell or whatever, those all on them somewhere will say something like 1.5 volts. That means that this battery can impart 1.5 joules of energy to every coulomb of charge. Okay? More positive charge at some point means more electric potential. We can make the analogy between electric potential and, say, height for gravitational potential energy, right? A positive charge that is near a high electric potential can fall away from it, like rolling downhill. Like if you put another positive charge here, because there's another positive charge here, there's a high electric potential in this region, and so it's going to move away from it. There's a lower electric potential here near the negative charge. But this is where that analogy falls apart, because if we put another negative charge here, there's a low electric potential here, and so a negative charge will sort of fall uphill. I know it's a little goofy, right? But you can kind of think of positive charges as uphill and negative charges as downhill. And that analogy ceases to work if you talk about free-moving negative charges, because they would roll uphill. In any case, there's no such thing as a negative mass, and so matter never falls upward away from a gravitational field, right? Anytime that there's some massive object, a planet, a star, whatever, it doesn't repel other masses. It just doesn't work that way. But electrons, on the other hand, are attracted towards positive charges or high electric potentials. And so they seem to roll uphill in that analogy. In any case, that'll do it for Chapter 22. Thank you for watching, and I'll see you in Chapter 23.